Everyone, and welcome to another edition of Basics to R. In this session, what we're going to be focusing on is we're going to be focusing on learning to use contrast statements in randomized controlled trials. So in terms of what we're going to be doing today, I'm just going to go through a brief review of what we've kind of talked about already in terms of understanding what randomized controlled trials are doing, how they work. We'll go over, again, the basics to RCT analysis, something that I covered in the previous video, and then we're going to focus in depth into contrast statements and then also go through some code that we can use to develop contrast statements for an RCT. Okay, so first, let's just briefly review what we've already talked about regarding what randomized controlled trials are. So first, what is a randomized controlled trial? So broadly speaking, a randomized controlled trial is wherein you take a sample of individuals in a population, you perform some sort of baseline assessment, you then randomize the population into one of two groups, an experimental group typically, and then a control group. And this experimental group can be something like exercise, it can be a medicine, it can be anything under the sun. And then the control group will not receive that intervention. And then we will look at, over time, whether the experimental group improved relative to the control group. So why do we run a randomized controlled trial? Well, broadly speaking, it's the best form of being able to determine the effect of an intervention. So, or it's one of the higher levels in terms of the actual evidence that we can gather. So just broadly, I'm sure some of us have seen this before, but in terms of an evidence period, at the very bottom of an evidence pyramid is going to be things like editorials and expert opinion. And so for the longest time in medicine, this was the expert opinion of philosophers, so people like Aristotle and Galen, who would opine on the different aspects of health and why people would be sick, or what would make people healthy. And a lot of times a expert can get things right based on experience and based on their own knowledge and existing time spent looking at a problem, but it's not systematic in any way, shape, or form. Then at a little bit of a higher level, we have things like case studies. So a great example of this is somebody like Phineas Gage, who I'm sure many of us know, was an individual who suffered a horrific accident that fundamentally changed their brain health. And so while these things are very, very interesting, they don't really tell us much in terms of what would actually happen in any sort of systematic way as well. Now, when we get into more modern science and modern scientific medicine, we have at the very bottom of our evidence pyramid, we have things like cross-sectional studies. Cross-sectional studies just take a group of individuals at one time point, and then we can look at how individuals within that group may vary according to underlying things that exist within the population. So, for instance, we might see that individuals that are more physically active or have a healthier diet might have lower BMI, and that would be a very simple example. At a little bit of a higher level of evidence, we have things like a case control study. Now, one of the disadvantages of a cross-sectional study is we are taking data at one point in time, and we're only measuring it at that specific time point. So it's hard to know whether individuals who have a certain condition or disease might be having that condition or disease because of some sort of exposure, or whether it's just some sort of reverse causation. So, for instance, individuals who have a disease like cancer might have lower body weight, but that doesn't mean that individuals who have low body weight are going to be more at risk for having cancer. Now, a little bit of a more sophisticated way that we can look at underlying conditions and understand how disease may vary according to different exposures is going to be a case control study, where we get two groups of individuals, one being individuals with the disease and the other group being individuals without the disease. And we can look at whether underlying characteristics within these two groups vary, and perhaps that may be a way of being able to identify individuals who may be at less risk of a disease based on the probability that looking at the probability that they might have a disease based on whether or not they have a certain underlying exposure. So, for instance, if we were to look at individuals with lung cancer, we could probably see that individuals with lung cancer, there would be a greater proportion of individuals who were smokers who had lung cancer than individuals who never smoked. Next, at a little bit of a higher level, though, is something like a cohort study. So a case control study, one of the issues with it is that in that study we are looking at things retrospectively, meaning that at that point in time people already have a disease or already have a condition. So there's a reporting bias that might happen in these types of studies, wherein somebody may have an underlying condition, but that doesn't the reporting may not necessarily reflect what happened to them over time. And so some way that we can actually really show causality is going to be something like a cohort study, wherein we can look at something in a more time-sensitive sense. So what that means is, for instance, in this case, is we look at a population and then we look at a specific exposure. So again, let's just focus on smoking, for instance. And we can see that a certain group of individuals over time will develop a disease versus people that don't have a disease. So again, sticking with that idea of smoking and cancer, we can see that over time individuals who smoke are more likely to have a disease versus individuals who don't smoke. And this would be how we can show temporality. Now, the issue is that with something like this sort of study design is, yes, while it's true that an exposure can lead to an outcome, there is the possibility that there could be confounders to this. And so the classic example is looking at coffee consumption and looking at the incidence of pancreatic cancer. We previously found that there was an association between greater consumption of coffee and greater likelihood of having pancreatic cancer. However, once we controlled for smoking, which is associated with both coffee consumption and also with pancreatic cancer, we find that there was no longer an association between coffee consumption and pancreatic cancer. And so it's important that we control for confounders in our studies that are looking at cohort studies. And while this is probably common sense, I think for most of us, the challenges with the cohort study is that groups are not randomly allocated. And so within a randomized control trial, what we can do is when we randomly allocate individuals to one of two treatment groups, we can actually show that any confounder assignment is due to random chance. And thus, these confounders are no longer an issue in terms of our ability to actually show that there is an effect of an intervention. Now, is a randomized control trial always the best study design to answer causal effects? Well, let's just go through a simple example. So briefly speaking, what we can see is that hypothetically, if we were to create a study design looking at the effects of an intervention, let's say to look at the effects of, using a parachute on loss of life when jumping out of an airplane. Well, if I wanted to look at that in a randomized control trial, what I would do is I would assess individuals at baseline. Yes, they're alive. Then I would randomize them into one of two groups, and then I'd look at experimentally whether the group with the parachute versus the group with the control were more likely to die from jumping out of an airplane. Now, this seems like a very obvious example of something like, why would we ever do that? Of course, individuals who have a parachute are more likely going to survive than individuals who don't have a parachute when jumping out of a plane. But the point is that we don't always need to have an RCT in order to show causality. We can show causality through other things. And so one of the simplest ways that we can do this is something called the Bradford-Hill criteria. And Austin Bradford Hill was an epidemiologist who worked primarily on smoking in the 1960s, and he provided a broad number of different types of evidence that we can use in order to determine causality, because the likelihood is that we're not ever going to do a formal RCT to look at whether smoking causes lung cancer, but we can show this through a number of different things, including the strength of the association, the consistency of the association, the exposure leading to a specific outcome. We can look at whether the exposure precedes the outcome. So, for instance, in the case of smoking, does smoking happen before somebody gets cancer? is there a dose-response effect? So if I smoke more, does that mean that I'm more likely to have a greater risk of lung cancer? There's a possibility of an exposure causing it. There's coherence with other established knowledge, so we know that smoking causes all sorts of other issues like atherosclerosis, etc., so it negatively affects our health. And then there's evidence from randomized control trials. In this case, we don't have that for smoking, but we do know that similar exposures cause similar outcomes. So other negative health behaviors also lead to negative effects as well. And the point is that if we can meet many of these criteria, then we can assume that there is causality between an exposure and an outcome, even if we don't have a formal RCT. And so this is something always to keep in mind when we think about why we actually do an RCT and what's an RCT good for. And so broadly speaking, just as again, like we talked about this last time, is in terms of an analysis of RCTs, one of the things I always like to keep in mind is that there's no perfect model. And so this is a quote by George Box, a statistician, showing who talked about how all models are essentially wrong, but some are going to be useful. And we have to understand that we're approximating nature. We're never going to actually get down to exactly what is the true association between a exposure and an outcome. Now, what are the things that we always need to include within our model in a RCT? First and foremost, we always need to control for baseline. That is something that needs to be included in terms of our model. Otherwise, we are going to run into trouble, as I'll explain in just a little bit. And secondly, we always only include covariates based on what could likely influence variation in our treatment effects. Okay, so why do I need to control for baseline? Well, I've explained this previously, but basically the gist of it is if baseline is not equal between groups in terms of an intervention at baseline, which is likely given the fact that individuals are randomized to either a treatment or control, then we may inadvertently decide that there is an effective intervention or there is not an effective intervention. So in this case, both groups improve over time at the same rate. So is there truly an effect of the intervention versus the control, or did the control group just start at a lower baseline? Next, on the other hand, we might run into a situation where the control starts really a lot higher than the intervention group, but the intervention group starts a lot lower. Now, this is a case where there's just regression to the mean that's occurring. So both groups are regressing towards the average. So this doesn't necessarily mean that there's a treatment effect. It could just mean that there's a regression toward that's actually happening. And then lastly, we most likely are never going to run into that situation that we would want where control and intervention are equal, and then we can actually show that there was a greater improvement of the intervention versus the control. But this is what we're trying to do within an RCT, is we want to be able to control for the fact that both groups have similar baseline values in order to be able to identify whether the intervention did indeed lead to improvements relative to the control group. And so this is why it's always important for us to control for baseline outcomes, as it will allow us to account for individual variation in performance at baseline, and it'll help confirm that improvement from an intervention is not due to chance or baseline performance. So should I include covariates based on significant group differences at baseline? Short answer is no. So in terms of randomization, what that means is it could mean that randomization is purely random. So any assignment that occurs through randomization is just going to be due to random chance. And so this is a good example of this. In each of these three different randomized groups or randomizations of groups, which one do we need to compare baseline differences? The answer is none of them, because we never need to compare baseline differences using hypothesis testing. Yes, it's good to know what those groups look like, but it's not something that we need to control for or base any sort of hypothesis testing on in order to look at our data. So here's a good example. So let's assume that we have a group of 200 individuals that we are going to assess at baseline looking at muscle strength. And then we're going to randomize the two groups. One group is going to receive exercise, the other group is not going to receive anything. Now, in terms of these groups, we see a number of baseline differences that exist between groups, including age, BMI, male to female ratio, educational attainment, cholesterol level, fat mass, reaction time, etc. Now, in this, does that mean that we should covary for each of these variables, given that they are all significantly different between groups? The answer is no. These differences are due, in fact, to random chance. And then secondly, what variables might be good to covary for in our analysis? And the answer is going to really depend on what you think is going to affect the intervention and the outcome of muscle strength. And so from my perspective, I would say that we likely need to control for age, BMI, probably male to female ratio, maybe something like fat mass and cholesterol level or something to that effect. Okay, so in terms of our RCT analyses that we can do, the classic example is the ANCOVA. So in an ANCOVA, we have a baseline assessment, we randomize groups to experiment or control, and then we follow up in a single assessment following the end of the intervention. Now, the ANCOVA is essentially asking whether at final assessment, do the groups vary after controlling for baseline? And so broadly speaking, within our example that we've made thus far, what we are looking at is whether muscle strength at final is different between groups after controlling for muscle strength at baseline in our covariates. Now, the problem with missing data in ANCOVA is that if there's any data that are missing at follow-up assessment in an ANCOVA, then these individuals are not going to be included in our analysis. And so this is a problem, especially if you're trying to adhere to the intention to treat principle. And thus, you're going to need to impute values at follow-up assessment when you do an ANCOVA if not everyone completed the follow-up assessment. In terms of another way that we can solve this is something like linear mixed modeling. Now, linear mixed modeling, we take that same sort of design, but we have multiple follow-up assessments now. Now, this solves the issue of missing data because with linear mixed modeling, we are now using something called maximum likelihood estimation, which allows us to estimate individuals who are missing across different time points in order to still include them in terms of our group means. Now, this, as I mentioned before, it's fine in this case if there are individuals that are missing at follow-up 1 or follow-up 2. Now, the challenge is that when there's more than, is that within this analysis, we're actually not truly controlling or including every single individual at baseline, but rather what we're doing is we're including them starting at follow-up 1. So that means that individuals who have data at follow-up 1 and follow-up 2 are being included. And this is because this means that it's really, really, really important that you try to have as many people complete your first follow-up assessment and your second follow-up assessment as possible. It does mean, however, that we're not, again, going to get everybody who completes baseline assessment. However, for the sake of, or what is commonly viewed in this case, is that individuals who are completing that first follow-up assessment are adhering to the treatment, and thus we can say that this is still following the intention to treatment principle. Okay, so in this case, what we're doing with a linear mixed model is we have an outcome at different time points labeled I, and we're looking at a group by time effect after controlling for a baseline outcome. And thus, outcome is really looking at outcome at follow-up 1 and outcome at follow-up 2 between each groups after controlling for our covariates. Now, again, muscle in our example, if we're looking at changes in muscle strength over time, then we are looking at muscle strength at follow-up 1 and muscle strength at follow-up 2 based on group. Next, in terms of random effects versus fixed effects, something that you might have already heard of, a fixed effect is a variable wherein it is assumed that across all levels, the effect on an outcome is constant. A fixed effect is assumed to be time invariant. That means that we're looking at something that is not changing over time. What happens at baseline is going to be the same across different time points. And thus examples of this are going to be intervention group, baseline outcome, and also our covariates. In terms of a random effect is a variable which is assumed to only include a random sample of the population, and many other levels may also exist. Within random effects, we assume that these are correlated over time, meaning that they are time variant. And the best example of this is going to be something like participant ID. Now, in terms of understanding the difference between random intercepts and random slopes, a random intercepts model sets the starting point for each individual, but the slope of the line is going to be the same for all individuals in that group. Whereas a random intercepts and slopes model allows each individual to have their own slope of change over time. Within a randomized control trial, at least in our own work that I do, there is very little likelihood that we're going to be using a random slopes model. The reason being is that you need a large number of time points, and you also need a large sample size in order to be able to run a random slopes model. And so thus for our purposes today, and typically within my own work, we typically do not run a random interception slopes model. We're really only working on interception. Okay, so understanding contrast statements. Let's talk a little bit about this. So first, when we conduct an RCT, what are we interested in analyzing? And the answer is are we interested in analyzing within group differences, between group differences, group by time effects, or D, between group and within group differences, or E, none of the above? The answer is that primarily what we're interested in is going to be between group differences. This is what is essential for determining the effects of an intervention versus control group. Now, we may be interested as well in within group differences or group by time effects, but really at the end of the day, what we should be interested in, and the primary purpose of an RCT, is looking at between group differences. Now, group of time by time effects are usually going to be unimportant. Now, what does that mean? So, broadly speaking, a group by time effect is really looking at whether there are changes that vary across time between the two groups. So let's give an example of this. So in the example on the far left, both groups are actually changing at the same rate. So there's going to be a non-significant effect of a group by time effect. But as we can see here, what we can see is that the intervention group is performing better than the control at both follow-up 1 and follow-up 2. The group by time effect in the middle is going to be significant. But again, this is actually really showing, in my opinion, regression to the mean. So yes, we do see a group by time effect, but that doesn't necessarily mean that this implies that this is somehow meaningful. And then lastly, the last one to the far right may be significant, it may not be significant. It's hard to know, like in this example, but what does appear is that there is a differential rate potentially that exists in terms of change from follow-up 1 to follow-up 2 for the intervention and the control. But it's not a huge amount, but there is something there. And so the point is that the group by time effect is only explaining the direction of the groups across time points, and may be only of interest in some contexts. What's going to be most important for an RCT is the primary endpoint. This is what's going to be the most interesting thing. So whatever that is, whether it's follow-up 1, follow-up 2, or follow-up 3, or whatever, the primary endpoint is going to be the most important thing that we're interested in within the context of an RCT. We want to know, was there an effect for the intervention between groups at time point, at the primary endpoint time point? Okay, so let's talk about what a between group contrast would look like. So let's stick with this idea of looking at an exercise intervention. We're looking at a resistance training group versus a balance and tone control group, which is a type of control group that is not performing exercise. They're performing like stretching and balancing exercises or something to that effect. If we're looking at trying to understand whether the two groups vary, so the resistance training group and the balance and tone group are different, then what we're going to be looking at is we're looking at whether the mean of the intervention group is different from that of the control group. And in terms of our basic statistics ideas, we're looking at whether the X bar, or the mean of the intervention, minus the mean of the control is different from 0. If it's not different from 0, then that would mean that we fail to reject the null hypothesis. So the null hypothesis is that these two groups are, the difference between groups is going to be equal to 0. If it is different from 0, then we would reject the null hypothesis, and then we say that there's a significant difference between groups. And this probably sounds familiar in some way, shape, or form to us. So, within an analysis of covariance, assuming that we're still looking at that same model, looking at differences between muscle groups, the first thing that we would do, is you might remember, is we're going to develop our estimated marginal means of each group. So we would look at what the means of the two groups are at final, and we would see, okay, the resistance training group has an estimate of 100 kilograms, the balance and tone group has an estimate of 80 kilograms in terms of their muscle strength. Then what we would do is we would conduct a t-test of some sort, looking at whether the two groups differ, and that would be equal to 100 kilograms minus 80 kilograms. We're just looking to see whether those two means differ between each other, whether there is indeed a difference that's larger than 0. And again, that's just going back to that same contrast that we're looking at of x bar intervention minus x bar control, and just trying to see if that's different from 0. So conceptually, the point of all this is to say that all of our statistical modeling is going to be based on these matrices that we develop. So in our matrix algebra, this is formally named, namely the formula of x transpose x to inverse times x transpose y. And so this is just the way that we would develop our betas within a linear regression. So yes, the matrix does exist, but in this case what we're really doing is we're developing a matrix of numbers that exist in terms of our different variables and looking at that in comparison to our outcome of interest, our y. So beta 1, beta 2, beta 3 are going to be all of our different components of our regression, and y is going to be our outcome of interest. And the same thing applies to an ANCOVA. Same idea, y is our outcome, and then our different rows or our different columns, that B1, B2, B3, are just the groups and the covariates within our groups. So as you can see here, there are different kinds of matrices. So the classic one that I show you on the left is a 4x4 matrix. That's just pretty easy to understand as 1, 2, 3, 4. So 4 rows by 4 columns, or by 4 columns. 1, 2, 3, 4. This would be a special kind of matrix called an identity matrix. It just means that one's going across the diagonal. And this is a 2x2 matrix. So 1, 2, 1, 2, 1, 2, 1, 2, 2x2. And a special kind of matrix that we can also do is a vector. That's a 1x2. So in this case, we're looking at a column vector, so 1x2. And this is really what we're going to be using the most of in terms of our contrast statements. So in terms of understanding our matrix algebra, the primary thing that we're going to be working with is going to be matrix addition and matrix subtraction. Now matrix addition, this would be an example of this where we combine two vectors into one. And as you can see here, it's 0 plus 2 equals 2, 1 plus 4 equals 5, 4 plus 3 equals 7, and 0 plus negative 1 equals negative 1. In terms of matrix subtraction, it's just subtraction going across the columns. So again, 6 minus 8, negative 2, 18 minus 1, 17, 8 minus 3, 5, 9 minus 7, 9 minus negative 7 is 16. So how does this work in terms of what we're actually trying to do? Now what we're going to be focusing on is, if we are still going back to that same idea of trying to look at the difference between groups in muscle strength, we're going to use this 2x2 matrix to develop a vector to look at specifically whether RT minus BAT differ between each other in terms of their estimates. So that would be 1, 0. That means I'm looking at the estimate for RT minus 0, 1. That would be the estimate for BAT. So it's 100 minus 80. That's all this is. So it's 100 is positive, minus 1 is 80. So it's 100 times 1 minus 180 times 1. So 100 times 1 minus 80 times 1. And so this is just a way of putting it all together into one simple way of looking at it, where again, all we're doing is we're looking at whether the intervention group differs between the control group, and whether that difference is different from 0. Okay, so let's look at this in a little bit more complex way now. Now, if I want to examine sex differences in the effects of RT versus BAT, how should I contrast this? So now I'm looking at whether the intervention for the males differs from that of the females. Now the way that I can do this is, again, I make a contrast statement going 4 rows or 4 columns for a vector. So now I'm looking at the effect for males. That's going to be 120 minus 90. So if we count 1 times 120, 0 means I'm not counting this. Negative 1 means I'm timesing that by 90. So it's 120 minus 90. So that will give me the effect for males, 120 minus 90, which is 30 kilograms. Then I'm going to subtract the effect for males, so 120 minus 90, for the effect for females. So this is going to be 0, so this is 0, 1, 80, minus, or 0 for bat males, and then -1 for bat females. So again, it's 80 minus 70. And so from here, this will get us our result, where we're looking at 120 minus 90 versus 80 minus 70. And so again, this vector is putting it all together into a single vector. And this is our way of being able to compare whether there was an effect for males versus an effect for females. So again, this is why we separate in our contrast statements. We're always going to try and separate it out into multiple contrast statements in order to make it easier to understand. Okay, so next what we're going to do is we're going to go ahead and we're going to actually run several examples of our contrast statements. And this will probably give us a better idea of how a contrast statement actually works. So first, I'm using the data that we've been working with in each of the videos. So I've already gone ahead and set up the data for both an ANCOVA and then also a linear mixed model. If you want a more detailed understanding of how you would do that, go ahead and watch the previous video. So just very briefly, here's what the data would look like for our ANCOVA. We have it set up to where we have these variables that we could include as covariates, so age, sex, education, height, weight, BMI, this variable for cognition called the ADIS cog, and then also something for looking at our physical function like the 6-minute walk test, which has been relabeled meters walked. And we have two groups, an intervention and a control group. Okay, so if I was going to set up just a basic ANCOVA model to look at this, what I would do is I'd first have to run the model in R. So I'm just going to go ahead and I'm going to go and look at it at time point 2, so that's meters walked dot 2. And then I'm going to add group, which is my grouping variable for intervention or control. And then, as I've mentioned before, we always need to make sure that we include baseline as a covariate. And so I'd go ahead and I'd run that. Looks like that's not available, so I just need to look again. Okay, I forgot to do something very important, which is include what the data are called. So again, data equals wide. Well, still not working. And that's because I put it in wrong like that. So need to do that. So now that that's all working, sorry about that, everybody. Now I can go ahead and I can look at a summary of the actual model. So this will be what it looks like. Now we can see that our meters walked baseline is significantly associated with meters walked at the follow-up time point, and however there's no significant effect for group. And again, if we were to look at our ANOVA table, we again see that there's no significant effect for group. And so this is going to be the telltale sign that we can see that there's no significant group effect. Next, if we actually wanted to figure out what it was in terms of the actual group differences, we would run the LS mean statement, as I've talked about before. We're going to run that same model looking at group, and we can see that in terms of the actual group differences, which so clearly I did not include a package. Sorry about that, everybody. So I needed to include the EM means package. So now that that's running, we can see that there's these two groups. There's the intervention and the control group. So we can see that the intervention group has a average of 356 meters at time point 2 versus the control group, which has an average of 300 meters. Okay, and so if I wanted to contrast this just the way that I mentioned last time, what we would do is we would again do the same sort of procedure. Looking at ls means, we're going to run that contrast statement that we talked about. Then I'm going to look at TRT versus CTRL, which is the call for looking at treatment versus control. And then we're not going to add any additional adjustment for multiple comparisons. And here we can see that there's a 54 meter difference, which makes sense. We can see that the intervention versus the control, there's 54 meters, but there's no significant difference between the intervention and the control group. All of this lines up with what we've already looked at thus far. Now, how can we look at, again, we talked about this before as well. We talked about how we can do contrast intervals. So all I'm going to do here is I'm going to run the same exact statement, but now I'm just going to save it. And now I'm just going to run this with the confident statement as well. And then this is going to get me the contrast parameters for the 95% interval. Okay, with a lower bound of 46.9 and an upper bound of 155 meters. So all of this probably sounds pretty familiar, but now let's get into how we can actually use contrast statements. And so this is going to be the same exact result. We're getting the same exact thing. And what I want you to focus on is I want you to focus on these two things. I want you to focus on the intervention line and then the control line. These are the two things that we're calling within the matrix. We're using the matrix of the ls means. The ls means is our matrix that we're calling. So the first thing that we're going to do is we're going to have to call up our model for, or our matrix for the intervention. So for this, I'm just going to call it C1, okay, for simplicity. And I'm going to call C1, and I'm going to look and say, okay, what I want to do is I want to call this. I want to call this line. So the matrix for the intervention group. So that first line is going to be a 0 because I'm timesing this by this, whatever's in the matrix here. And then that second line is going to be a 1. So 0, 1. And that's going to be our contrast 1 to look at, to say, okay, I'm looking at the intervention, the effects of the intervention, or I want to see what the ls means is for the intervention group. Now, let's do the same thing for our control group. So now it's just going to be the opposite. Two groups, so now 1, 0, because now I want to call this. I want to call this line. So now I have C1 and C2. And now let's just say that I want to look at the contrast of C1 versus 2. So I'm just going to call this con1, and this is going to be C1 minus C2. Okay, so now we have all that set up, and now all we're going to do is we're then going to call that contrast using the same statement that we used before. So we're now going to use contrast ls means, but this time, rather than calling the complete model that we did before, there's going to be one little difference. Okay, so now we're going to do the same thing right here, and now we're going to use something called the list command. The list command is then going to say, okay, I just want to call this contrast statement that I wrote, and then I'm going to use this command by equals null, and that's it. So now if I run this, I'm going to get the same exact result. And if you look here, it is in fact the exact same result. So this is the contrast that we used with our contrast statement before, and now we're doing the exact same thing all over again. We're just using the numbers for it. Okay, so it's the same exact thing. We're looking at 0, 1 minus 1, 0, and that's giving us this con1 statement. And that statement is what we're calling here, and that is just to look at the difference in the means between the intervention and the control group. That's it. So that's a pretty simple example of how we could do this. But now let's make it a little bit more complex. Now we're going to look at whether there are sex differences that exist. And so to do that, we first have to write our model looking at sex differences. So in this case, let's just go ahead and we're just going to call lm meters walked dot to again, but this time we're going to have a group by sex effect. Okay, then we're again going to include meters walked at baseline as our covariate of interest, and then we're going to call our data because I forgot to do that last time, and then that's that. And now we can go ahead and we can do the same thing that we did before. So first, let's just go ahead and we'll look at the summary command. Okay, we can see that at least from this level, it doesn't look like there's going to be any sort of group by sex effect, which is not that surprising, given that there was no main effect. And again, we're looking at the same thing. There is no significant difference, but nonetheless, let's just go ahead and let's continue to look at this. So first, we're going to go ahead and we're going to call our ls means looking at group differences by sex. So we're going to go ahead and we're going to call group by sex, and that's going to give us our ls means. Okay, and now what we need to do is we need to develop matrices looking at the intervention for the control for females versus intervention versus control for females, and intervention versus control for males. And we're going to compare the effects for females versus the effects for males. And so to do that, let's just go ahead and we're going to do our new matrix, which we're just going to call females. So this is going to look at the effects for females. So again, I am going to populate that matrix. So I have 4 numbers that I can include here. And so I'm not including males, so we can assume that these two are going to be zeros already. But now I just need to think, how am I going to set up my matrix for the intervention versus the control? Well, in this case, because I want to compare the intervention versus the control, it's going to be a positive number versus a negative number. So it's going to be -1 for the control, a +1, so and then a 0 and a 0. So let's go through that step by step. -1 right here, +1 here. So this means that I'm timesing -1 by this number, or by the control group, and then I'm timesing +1 by the control group. So this is giving me 349 minus 275. So that is the effect of the intervention versus the effect of the control. And I don't want to include males in this because I'm not looking at the effects for males. Then, what if we wanted to create a matrix looking at the effects for males? Well, again, males, if it's males only, we're going to exclude females. So these first 2 numbers are going to both be 0 in our matrix. And then we need to create that positive and negative number matrix. So again, it's going to be the same thing. -1, +1. So -1 is going to be for females, +1 for males. So now we're looking at 377 minus 34. And that's it. So now we have our contrast statements for our females, and we have our contrast statements for our males. But what if we want to look at the contrast between males versus females? To do that, we're going to do the same thing. We're going to just set up what we did previously. So now, if I want to create males versus females, I can do it either way. I'm going to just do it this way, males minus females, and that's going to give me my contrast statement for the effects of the intervention for males versus the effects for females. So now that I have all this set up, now I'm going to go ahead and I'm just going to develop that contrast statement. And so now I'm going to use ls means again, and then I'm going to do model 2, and then group by sex, and then I'm going to list the group, the males versus females, because this is the one that I'm interested in. I could also list as well females and males too. Okay, and now what you can see is I get these I get each of the contrasts. So this first one is my contrast for males versus females. And so if we were to just plot this out, we could see that this is in fact makes sense. So first, as we noted before, that for females, there was roughly about a 75 meter difference between the intervention group and the control. And for males, it was a 43. So 377 minus 334 is about 43. And so we can see that these are the effects for the males. These are the effects for the females, for females in the intervention group versus females in the control. Then, if I want to look at the effects for females versus males, it's just males minus females. And so 43.5 minus 74.3 is negative 30.8. And that's it. That's how we run a contrast statement. I'm going to go ahead and let's go through how we would actually come up with a contrast statement for a linear mixed model. So first, let's just take a look at the data. So now, as you remember, we're looking at data that are being looked at across time. So we have our baseline variables, which are now being looked at separately, and then we have these time varying variables for 8 days cog and meters walked, and time varies only at time point 2 and time point 3 in this data set. So first, let's just go ahead and let's come up with that linear mixed model for our looking at the group by time effects for meters walked. So to do that, we're just going to come up with this model, and we're going to use the package Elmer. And again, we're just looking at group by time. So time is being treated as a factor here. And then we're just going to only include baseline in our model. Okay, and then we're just going to look at data 3 because that's our data that is time varying. Now, and again, we're including the random intercept within our model. Okay, so we now have that model. We can just look at it really quickly. Here's our summary, and then if we want to look at the ANOVA for it, this is what we would get. But that doesn't really tell us anything in terms of being able to see whether there are time effects. And again, our primary endpoint for this model, let's just go ahead and assume it's time point 3. So to do that, we're just going to go ahead and we need to use that LS mean statement. Again, we're looking at model 3, and then we're going to go group by the factor of time. And now we have the same thing that we had before. So we have time at 2, intervention versus control, and then time at 3, intervention versus control. So how would we go about figuring out what the contrast is for time at time point 2 versus time point 3? So if we were interested in looking at time 2, then we're just going to go ahead and we're going to develop that matrix looking at the differences between groups at time point 2. So for that, again, we're going to assume that we're looking at intervention versus control. So intervention is positive, control is negative. So it would be -1, 1, and then 0, 0. And that's at time point 2 because, again, we're just looking at whether the intervention did better than the control group in terms of meters walked. And then at time point 3, same thing. We're going to look at we're going to not include the intervention or control at time 2. And then we're just doing the same thing where control is being treated as negative and the intervention is being treated as positive. And now, because we're interested in the primary endpoint, again, we can include both of these for right now, but our primary endpoint is going to be time 3. We would just go ahead and we would develop that contrast statement, looking at LS means for model 3, looking at group by factor of time, and then looking at treatment versus control, or excuse me, we would then use that list command, and then time 3, and then we're going to go by equals null, and again, we're not going to adjust for anything. And it looks like we just have a minor issue here, so just give me 1 second while I figure that out. And I didn't have a parentheses right there. And then, as we can see here, we now have our effects at time 2 and our effects at time 3. So again, for our effects at time point 2, we would see 346 minus 312, so that's about 34, and there it is. And then for time point 3, same thing. 359 minus 323 is about 36, and so we can see that those are the two differences. And again, we're just looking at the two different time points. So this is how we would do is we just need to create individual matrices. Now, this gets especially more complicated if you start thinking about group by sex differences and things like that, because now our matrix has to go from 4 up to 8, since there are two different sexes and we're looking at the differences at each time point. So keep this in mind when you're developing your contrast statements, and oftentimes it's much easier to write out your contrast statement first rather than trying to develop it all at one time. And that's totally fine. You have to take your time with these things and it will work out a little bit better. And as always, if you have any questions, please feel free to email me. I do have practice problems and things that I'll go through in a separate video here in just a minute. So thank you again, and hope to see you soon.